Welcome, everybody, to our webinar of pymc Labs with Jesse Grabowski. I'm Thomas Wiki, your host. I'm the founder of pymc Labs and one of the authors of pymc. And well, this really is the culmination of a lot of effort that went into pymc to really make it support time series better. And as you probably know, structural time series modeling specifically has a lot of value when done in a Bayesian framework and offers a lot of flexibility to impose structure onto your time series. And for the longest time, this has been sort of a bit of a sore spot in pymc, but Jesse has been pushing hard along with Ricardo and a lot of the other pymc developers to make that happen. So really excited to have him here today. Jesse, welcome to the show.
Yeah, thank you so much. And it's been a long road. This was actually the subject of my very first inroad into the pymc community. So I went from clueless guy posting on the Discord to presenting at the pymc webinar. So there you go, the full zero to hero. Well, the hero remains to be seen, but I'll do my best.
Yeah. That's great. And also, of course, welcome to everyone who is tuned in. Really great to have so many folks here. If in the chat you just want to write where you're calling in from, that'd be great just to get to know a little bit better where you're from. And California, nice. Guess that's just getting started. Baltimore, Arizona, New York City, Orlando, Italy, Paris, Munich.
I saw Paris. Shout out to Paris.
Oh, yeah. Are you in Shanghai or are you in Paris currently?
I'm in Shanghai, but I am a PhD candidate at Paris 1 in the economics department. So
very nice.
I'm throwing my arms around Paris.
Yes. Argentina, nice. Well, thanks everyone for joining. So before we get going I guess, Jesse, what is your origin story of coming to Bayes, to pymc, to time series modeling? Why that topic in particular, and why in a Bayesian way?
Well, for sure. So Bayes, I was trained in a very frequentist econometrics background, doing stuff like in Stata, right? Reg YX, comma, VCE robust, like running diff and diffs. And this was back in like 2016, 2017, when machine learning, like 1.5 was like really hot, and like doing a random forest regression was like the coolest thing you could do. So I thought, like, man, I don't want to do any of this 80s stuff, regressions. Like, what is that? I want to learn machine learning. I want to learn deep learning. I want to learn the real stuff. So I got into that. I took some courses and I got disenchanted with that because you fit a big neural network, you get some weights, and it's cool, but you can't say anything causally. And it wasn't helpful in a research setting as an applied researcher in economics. So I kind of circled back around and said, what else is there out there that can give you this freedom to model as you please, that isn't just inverting matrices, but then at the same time gives you understandable, causally sensible outputs? And that led me to Bayes, that led me to pymc, that led me to UDaPearl and McElrath. And here I am. Time series, because I like to torture myself, I guess. Like I was told in a course once, like as a quip, that like time is somebody else's problem. Like applied researchers, do a cross section, like you do a panel, throw some dummies on the years to sort of soak up the time variation. But like what you're interested in are stable effects that aren't necessarily going to need these heavy duty time series things. And maybe that's true, but in a lot of cases it's not. And especially in low data regimes, if you're interested in studying development economics and you want to know about sorghum forecasts in Senegal, like, well, there's not a lot of data, so you need to bring a lot of structure to make up for the fact that there's not a lot of data and enter structural time series modeling.
Yeah, I love that. And certainly resonates strongly, especially the causal component. And I sort of am getting more and more to this realization, I guess, that the best thing about Bayes is not that it's Bayes, but rather that it's a really great framework to build causal models in.
Yeah.
And time series is like a very
Right.
related
It's the
one.
universal estimator, right? That's a McElrath quip that like we only have one estimator, it's the posterior. And that's the power of Bayes. Like everything else is like it's interesting. It's it's fun to talk about priors, it's fun to talk about hierarchy, but at the end of the day, I just never want to have to develop an H0 ever again. And I don't have to because I just sample the posterior and do whatever I want.
Yeah. And that's also, I mean, now I guess looking at the experience with pymc Labs and all the consulting projects we've done is really at the core of the value that we deliver. It's not that like, oh yeah, you have uncertainty and priors and like all the standard things, but really, well, yeah, we can take your business problem and map that accurately into a causal model and then like really analyze the data, how you know these things are connected with each other.
Absolutely.
Well, great. So yeah, I don't want to take too much time away from what you have to show us today. So feel free to dive in. To the audience, there is you can either put things in chat, but actually it's easier if you put them in the Q&A box, and we'll get to them after or maybe during if it's relevant. And yeah, thank you, and
All right.
looking forward.
Cool. So I have an ambitious agenda. I prepared 4 notebooks. We'll see how far we get. But the theme is going to sort of be, we don't need to know who I am. The agenda for today is sort of what is time series modeling look like in pymc. So I'm going to start with doing it by hand. And I'm going to assume that you have some background knowledge in pymc, that you kind of know what an ARIMA model is, what a var is. If you don't, I tried to be as verbose as possible. All of these notebooks will be available on GitHub. They're not available now. I was panicking and trying to upload them, but I didn't make the deadline. So we'll look at how it looks in pymc right now. Thomas mentioned that a lot of people are working on this. And what I'm working on in particular is this statespace submodule, which is a wrapper around this functionality that we're building into pymc that makes things really easy. Well, easier and try to be a bridge between the flexibility and the power of pymc to define priors and to be really creative with your priors, but then also to not have to worry about what's a Kalman filter, to not have to worry about what's a scan, how do I do differentiable recursion on a directed acyclic graph. You shouldn't need to know any of that if all you want to do is forecast the sorghum harvest in Senegal. So, but I'll start with just showing you sort of how things look by hand, just as a point of departure, but then we'll hard cut to the statespace module and we'll see how to do it using that and how much quicker and easier it is and all of the powerful things that come along with that. And there are things you can do in the statespace module that you can't do in full control mode. From there, we'll shift gears and we'll look at VARs, which is sort of the multivariate extension to ARIMAs. And we'll see how to do forecasting and also how to do impulse response functions, all kinds of different Bayesian impulse response functions with just one line of code. Very easy, very convenient. From there, we'll pivot to structural time series modeling with exogenous variables and scenario-based forecasting. So another big topic, especially thinking about marketing, thinking about when you have control variables like market spend, how can you integrate these into an ongoing time series process? So on one hand, you have these non-time varying things that you're injecting into the system deterministically. You're choosing to spend money, and that's going to push the system, but the system is also running through time at the same point. So how can we do all that together? And finally, I have my extremely ambitious nonlinear DSGE model I promised in the advertisement. It's, we'll see. I'm quite proud of it, but we'll see. And the link is here. Okay, so why time series? Time series are great. Everybody should be working with time. I made a quip earlier, but they are a pain to work with. And the purpose of pymc-statespace is to alleviate some of the issues. What are those issues? Model selection. You have to do a lot of handcrafted code just to get, an ARIMA 1.1, and then you want to go to, an ARIMA 3.1, or you want to add seasonal components, and then what do you do? Well, you do a lot more hand coding. Getting outputs. What kind of outputs do you want? Do you want unconditional posterior distributions? Do you want conditional posterior distributions? Do you want impulse response functions, forecasts? The way that pymc is set up, this is actually quite onerous to get each one of these things. You need another handcrafted out of sample prediction model in order to get each one of these. And we'll see that you can skip a lot of that. Handling mixing data. This is something that Bayes promises to do, and it does do very well in the cross-sectional regime. But in the time series regime, it's more complicated. You're iterating through time, you're feeding in an observation and creating a prediction, and then feeding in an observation and creating a prediction. You get to a point where you have no data to feed in. What do? You need to marginalize over that hidden state. You need to take this observed distribution and say, well, now this is a hidden state. I need to marginalize over all the possible values it could have, and then take another step forward and carry that uncertainty forward. Trivial, but statespace can do it for you. And then this question of how to mix time structure into like a normal regression, where you have sort of this YT model, which is just a normal linear regression, XT on beta, XT times beta on Y, but then you want to have these errors which have some kind of time series structure to them. So we'll see how that works. Oops. Sorry, this poll is trolling me. Someone save me. Boomer Jesse is having a hard time. Okay, let me just go faster. So a motivating example. So here's my definition of a time series model for this, the purposes of this presentation, and it's going to be this, where you have xt is equal to g of xt minus 1 and epsilon, where xt minus 1 is the state of a system at time step t minus 1, and then epsilon t is some stochastic innovation to the system. So, and g is what I'm calling a policy function. And once you know the policy function, then you have a recursive model that you can just keep applying. I know what the system is at xt. I receive some information from the world in the form of these epsilons. I sort of put that information together, and then I apply this policy function, and it updates the state of the system. And you can just recursively apply that. So you can have g of g of g of g of xt, and that gives you your xt plus 4 forecast. Okay, so sort of as a motivating example, we'll use an ARIMA 1, which looks like this. You have xt is equal to rho of xt minus 1 plus some epsilons. So our policy function is very simple. We're just going to take what we see, we're going to scale it down a little bit, we're going to add some noise, and then we're going to step forward into the future. Have to make some assumptions. The most common one is that these epsilons are IID normal, means 0, variance sigma squared. So we have to model rho, we have to model sigma, and then we have to model x0, kind of the starting position of the system. How does this look in pymc? It's pretty gnarly, but it's not so bad once you get used to it. Here's your boilerplate about setting up coordinates, and then we're going to open a pymc model. I'll define a prior on rho, which I choose to between 0 and 1, because I want the system to be stationary. We'll come back to that idea. Strictly positive prior on sigma, uninformative prior on x0. And then we need to write this wrapper. What this wrapper does is it defines a recursive probability distribution over an entire sequence of observations. And you can see inside we're doing this pytensor.scan, which is our structure for doing recursive computation. Scan takes a step, which is going to be the inner function, the thing we're going to apply again and again and again. And you see inside this step, I have my policy function. So I'm going to do an update. I'm going to return the new xt, and then I have this more boilerplate doing collect default updates, which is something that you really don't need to know about unless you want to come be a developer, but you have to include it. And then you return the sequence. Then you use this thing called custom dist, which is another thing you have to know about. Go read the doc strings again. And then finally, we can sample a prior. So all of this for an ARIMA 1.0, which is pretty heavy. But it works very well, and it's very flexible. Here's a sample trajectory. So I just sampled from the prior. I chose one of the 500 prior draws at random. I'm saving the true parameters so that I can see if I can recover them later, and then I'm plotting the sample. So this will be kind of our data that we're going to use to model. And there's a really cool feature in pymc. You can use this pm.observe. And it actually is a model transformer. So I give it my model and I tell it what variable I want to make observed and what data I want to give to the observation. So this variable obs, which I defined above as the data distribution, the output distribution, will now be an observed distribution using this sample. And then I can just call pm.sample to get my posterior. It samples quickly, and you can see that I do a reasonable job recovering the true parameters. Now, what we want to do, though, is we want to forecast. We want to get posterior predictive samples. So what you do in pymc is you open a model. Again, here I open my observation model, and I call sample posterior predictive. And then I get this, and I wonder, did this even fit? Yeah. Is this really my posterior predictive? And the answer is yes. It's just, it's not maybe the distribution that you were expecting. You may have been expecting something that's tighter and moving with the data. And that's what I call a conditional posterior distribution, where you're doing one forecast, you're saving the one-step forecast, and then you're throwing it away, and you're taking the next data point, doing one step, taking the next data point, doing one step, and then accumulating those one-step forecasts. What this is doing is it's showing you all the possible trajectories that could have happened had you started at x0 and then let the system evolve for all of these time steps. And that's why we get this fat, narrow band that doesn't seem to follow the data at all. But I assure you that 94% of all of these data points are inside of this span. So it's kind of this unconditional posterior distribution. How would you go about getting a conditional posterior distribution? Well, there's an entire new tutorial on how to do that and how to build a secondary model and how to change the inner function to scan in order to get that. But it's outside of the scope of this presentation. I do recommend that you check out this tutorial that was very, very well written. What we can do instead is we can use the state space model. How does the state space model look? It's built to follow stats models. So everything should look quite familiar. Instead of making, well, before making your usual pymc model, I'm going to import state space, and then I'm going to create a Bayesian SARIMA. And the Bayesian SARIMA has a bunch of arguments. I give it an order. So in this case, 1, 0, 0, 1 lag, 0 differences, and 0 moving average terms, so no lags of the errors. No seasonal structure, and then some other arguments you can read about in the documentation. But this creates this state space model object. And when you create a state space model object, you get these instructions. It says you need to make a pymc model, and you need to declare priors on 2 variables. One is AR params, which has a dimension AR lag, and one is sigma state, which has no dimensions. So now we just have to follow instructions. We open up a pymc model. We declare the 2 parameters that were asked to declare back state space graph, and we give it data. And what we'll do is it'll go into the P model that we've built for the says, did you params have the right dimension, the right dimension? To do a pre-calculate you want up to that point. You could have a very complex hierarchical structure before you get to AR params, m.nistic AR params, em.normal AR param, find that name, you're good to go. So in this case, get back a model that's quite simple, look at this. You have 2 variables. The 2 variables are put into a Kalman filter, and then your data is generated. So then you just sample as normal. You call your AR1, and then you call pm.sample. One side, I strongly recommend that you use jack-based samplers for working with the state space models. We're still working hard on getting these scan-based recursive algorithms, these heavy algorithms like Kalman filtering to be quick in the default C backend. But right now it's like a 1,000 times difference. So I sample with NumPyro. It takes about 4 seconds. And yeah. I thought the next slide was outputs. So I said, yeah. A couple important details. So every state space model comes with coordinates. And all of the coordinates, there's some default coordinates. You get these states, observed states, and shocks. And then there will be special coordinates for each model. So in this case, we have the AR lag coordinate. So always remember when you open your model to chords equals SS mod chords. The second important detail was this build state space graph. You always have to build the state space graph because that's what signals to Python that you're ready to take these random variables and insert them into your system of equations. So in the background, and we'll look at this a little bit more, you're quietly building this system of structural equations. And this system of equations knows where it wants to put things based on their names. It's just waiting for you to provide that information. The way that you signal that you're ready to give it is with build state space graph.
Hey, Jesse, do you want to switch off your camera to preserve
so
a bit of bandwidth?
Yeah, sure, can do. Let me just figure out. Okay.
Great, thanks.
So as you can see, we get exactly the same parameter values. This is the same model as we fit before with the scan and the inner function stuff. But now we've gone from 20 lines of code to just 2 or 3. But what we also get, what's more important, is that we get access to a number of powerful post-estimation sampling functions. So typically we're going to want to look at posterior predictives, we're going to want to forecast impulse response functions. And we saw before that it's not always obvious what you're going to get, but when you're using this state space module, it is. So if you ask for unconditional posteriors, so I call my state space mod, I call sample unconditional posterior and pass in my inference data. It's going to sample, and it's going to give me back an iData that has the posterior latent variables, so the hidden states, and the posterior observed states. So right away, you're able to recover hidden states. You're also able to, it'll also generate for you the observed states that are associated with those hidden states. And we see that this is exactly what we got when we sampled from the first model. Not so interesting, but we can also ask for the conditional posterior samples, which is probably what we wanted all along. So the only change is the helper function that I call, instead of mod.unconditional posterior, I ask for sample conditional posterior. And I pass in exactly the same iData. Once again, well, what I get back is a little bit different. So instead of just getting the hidden states and the observed states, now I'm getting back 3 different types of outputs. And these are 3 different types of outputs generated by this Kalman filter that's going on in the background. I get the Kalman filtered posterior, both the hidden state and the observed state. I get the 1 step ahead predictions, and I get the Kalman smoother outputs. And we'll sort of look at what those mean and what those differences are if you're not familiar with this. And here's how it looks. This is probably what you were expecting to have gotten in the first place when you first modeled a time series in pymc. So you can see that it sort of dips and moves with the data. It has that characteristic 1-step delayed behavior that an AR1 should have. So again, another important task, probably the most important thing you want to do with time series, is forecasting. And again, forecasting is made easy. You just call ssmod.forecast, pass in the initial data, and tell it for how long you want to forecast. So in this case, I'll do a 50 period out forecast. By default, it's going to start at the last index on the data. You can ask it to start anywhere though. So if you wanted to do like a hedgehog plot, for example, you could forecast at time 10, 20, 30, 40, 50, and you could get a 10-step ahead forecast starting from each of those positions. It wouldn't be a true hedgehog plot because you would have future information when you were doing the like quote unquote forecast at time 10. Like the time 10 is fit with parameters that were fit with information at time 50. But it's close and it's fast and it's easy. Once again, you get back both the latents and the observes, and we can see how it looks. Bang, there you go. So automatically it's going to add the dates on for you. And it's just going to apply this policy function again and again iteratively forward through time. So an AR1 doesn't have a very exciting forecast. There's only dynamics for 1 time step. So you see we were kind of above the mean. And then within sort of 1 time step, we return to the mean value. And then we just have a constant steady state prediction for the rest of time, which is what an AR1 does. they're not that interesting. Okay, so what is happening under the hood? So if you do this by hand in PyMC, you are able to implement any model that you want with any stochastic innovation distributions you want. If you want a Poisson state space, no problem. If you want nonlinearities in your policy function, no problem. If you want a space model, the state space module, you're restricted to linear Gaussian models, specifically models of this form. So we have a transition equation xt, which is sort of this policy matrix that's transitioning us from xt minus 1 to xt, plus a bias term, plus the stochastic innovations, and then an observation equation with potentially measurement error here. And then both, whoops, excuse me. And then both the innovations and the measurement errors have to be normally distributed. So this seems pretty bad. Oh, here's all the objects and what they mean, by the way. This seems pretty bad. It seems pretty limiting, but actually is not. You could do a lot of powerful things with this. And in a lot of cases, this is where you're going to want to start anyway. So it's a pretty good trade-off. And we'll see, you can even do nonlinear models in this framework. You just have to linearize them first. Oops, okay. So the way that all this works is it's under the hood running a Kalman filter. A Kalman filter is a Bayesian algorithm. It's a way to iteratively update your belief about the state of a system whenever new data comes in. I'd say it's not so complicated. It's not rocket science, but it literally is rocket science. This is the GitHub repository for the Apollo 11 guidance computer. And you can see that there are Kalman filtering algorithms that were running on the Apollo 11 spaceship that took astronauts to the moon for the first time. So this is a framework that has a very long and storied history, and I don't know, it makes me proud to be a little bit of in that history. Okay, so when you're using a Kalman filter, it's very easy to do that hidden state marginalization that I mentioned. If you're missing data, the Kalman filter has no problem with just switching on Earth to being unobserved. So if you have holes in your data, it's no problem. To drive this point home, I'm going to drop 20 observations from the middle of the sampled series like this. I'll just set them to be nan. And then I call the model exactly as before, just putting in the data with missing variables. You'll get a warning that it has missing variables and they're going to be imputed during filtering. But once you get it back, you're allowed to do all the same post-estimation tasks. I call for the conditional posterior. And then you can see here was the area with the missing values. So this is the one step ahead predictions. So it's kind of like starting from where the missingness happened. We just did forecasting. We just forecasted for all of these periods. And because we're an AR model, that's not so exciting. But then when data came back, we switched from this forecasting mode back to our filtering mode. We can do better though. So if we use this smoother, so the Kalman smoother takes into account the best predictions given all the previous information up to time t, but it also it goes backwards. So it also takes into account future information. And so you can see that when we get to be missing, we're down here. And so we get these AR1 dynamics coming back up to the mean, but then the smoother knows that in the future, we're going to go up again. So we also get some AR1 dynamics coming back up on the other side. So you get slightly better hidden state inference in these missing patches by using a Kalman smoother. And we'll see more applications of the Kalman smoother when we look at models with entirely unobserved states in the DSGE. Okay, so that's kind of like the crash course, yeah? All you have to do is declare this Bayesian SARIMAX object. You ask for an order, a seasonal order. You do what it tells you to do in a pymc model, and then you hit the sample button. There's a lot more complicated stuff you can do with this. Just as by way of quick example, if we wanted to compute stationary covariance, we could grind through some algebra and I'll spare you. But what you get down to it is that if you have a stationary system, then the covariance matrix is just going to be this this sigma x, which comes out of solving this discretely Lyapunov equation. And we actually have a function that does that in pytensor. And so you can actually do that with your state space model. So if you were so inclined, you can open a new model. You call build dummy graph, and I'll show you what a dummy graph does in a second. You call insert random variables, and that's going to take these dummies and put them into your state space matrices. Ask for your state space matrices with unpacked state space, and then solve your discrete Lyapunov equation. And then compute deterministics. So what did this do? It created two flat priors, and then it inserted those flat priors into the state space, the state space matrices that form this linear Gaussian state space. And then it's doing a deterministic calculation to find the stationary covariance. They're flat because we're actually not going to use these priors. PyMC, when you compute deterministics within an inference data, it throws away the priors and instead samples from the inference data. So we're actually not computing with flats, we're computing with posteriors. You could put anything here, not just flat. I put flat because if you can't sample from a flat. So if there's an error, then PyMC will say something went wrong, you can't sample from a flat. And so here is the distribution over the covariance of the stationary system. So it's quite nice. It's very powerful. It's very flexible. But that's univariate models. So I want to shift gears now and look at multivariate, which is going to be in a var. Whoops, start at the end. So var is a multivariate extension of ARIMA. So I assert to you that this is a multivariate ARIMA. It's ugly. I mean, these are objects that only a statistician could love. But if you sort of squint and turn your eyes sideways and you define a state like this and a coefficient matrix like this, you can get a recursive equation that looks like this. And this is exactly what we need. This is exactly our linear Gaussian state space setup with the T matrix as this gamma. Now, this isn't exactly what a var looks like because if you wanted more lags, it's more complicated. And I've linked an example notebook that really goes through what the true transition matrix looks like in a var. But this is kind of the broad idea. We have multiple equations, multiple variables that we want to track, and all of the variables are going to be functions of all the other variables in the past. Okay, so for data, I'm going to take some US macroeconomic data or for GDP, private consumption, and private investment from 1959 to 2009. And I'm just going to do some pre-processing on it. It's not super important. But here's what the time series look like. So our hypothesis is that GDP is a function of GDP in the past, but also household consumption and investment, which is true by definition because GDP is defined as the sum of consumption, investment, and government spending, right? But also that there's relationships within the other ways, right? So consumption is a function of GDP. The better the economy is, the more people consume. Or that investment is also a function of GDP. Some similar argument about when times are hot, you're going to buy more Doge coins, and that's going to work out great for you. So it is possible to do the same exercise by hand, and there is an example notebook for how to do that. If you go to the PyMC example gallery, here's how it looks though with our state space setup. So you're just going to call Bayesian varmax. You're going to ask for a 2-0. So again, it's the same P. 2 is the lags in the states, and 0 is the lags in the stochastic innovations. Now I'm going to give names to the states. So I tell the columns are the names of the variables, and then some other things. There's this thing called stationary initialization, which I set equals true in the ARIMA, but I kind of glanced over it. You always have to tell the system, where did you begin? What was your x0? And because we're Kalman filtering, we're iteratively updating not only the state of the system, but also the covariance matrix that describes the errors in the system, we also have to initialize the covariance matrix. And these are just nuisance parameters. We really don't want to think about them. So when we can, we just want to set them to the steady state. We want to set them to kind of system go back to if there's no shocks. So if you promise, if you pinky swear, cross your fingers, that you will not give a diverging system, then you do not have to initialize x0 and p0. The trouble is with a var, it's extremely difficult to do. So here I pinky sweared that I was going to give a stable system, and then I want to do a quick stability check. So the condition for a var to be stable is that all of the eigenvalues of this matrix T lie within the unit circle on the complex plane. So I'm using this helper function sample state space matrices to say I want to take samples of the T matrix using my prior. And I'll save that as prior T. I'm very clever. And here's what I get. So it looks like the Death Star exploding, which is not what you want to see. Sort of. I guess it depends which side of that you're on. But the black circle is the unit circle. And for the system to be stationary, to be stable, to not explode to infinity when you shock the system, you need all of these dots to be inside the circle. And as you can clearly see, we just took draws from a normal 0, 1 to be our initial parameters for the lag coefficients. And it's just a mess. Yeah. So it's really not trivial to end up with a stationary var. So vars require some careful thought when you choose your priors. And we haven't figured out a good way to give you tools to do that easily yet. So just be careful is what I'm trying to say with this presentation. The easy way is to just don't promise that your thing's going to be stationary, yeah? So I just say stationary initialization false, but now it tells me you need to tell me an x0 and you need to tell me a p0. And that's fine. So I create my pymc model. For x0, I'm just going to pick something close to 0 because what I would like is for my system to be stationary. And if it were stationary, x0 would be 0. That's my logic. For p0, I'm going to use a diagonal covariance matrix. And remember, I told you that you can do as much pre-calculation as you want, as long as you end up with the right name at the end. So what we're going to end up with is p0, and it's going to be a diag of this p0 diag. P0 diag is, I used this find constraint prior, which is a very nice function. It's going to get me a gamma that has 95% of the probability mass between 0.5 and 0.2. I chose those numbers by looking at the plots. They kind of go between, plus or minus 2. That's how I came up with 2. And I figured, okay, what the heck? Let's also upgrade the shock covariance to be dense rather than diagonal. So I'm going to use an LKJ Cholesky covariance prior to make the shocks between the different states. So we're going to allow for the innovations to GDP to be correlated with the innovations, for example, to consumption. As before, I call build state space graph. I'm sampling a prior, and then I'm also sampling posterior with numpyro. And you see it takes a little longer, 3 minutes to sample this one, but still reasonable. It's for a var2. I'd say performance is okay up to systems of about 20 to 50 states and time series of about up to 1,000 time steps. Like once you get beyond that kind of medium size, performance is still an issue. So help wanted, if anybody is tickled by this presentation, wants to give us a hand, I would absolutely love it. And here's our results. So sampling went well, our chains look like nice fuzzy caterpillars. You can see that the off-diagonal terms of the state covariance are meaningful. Why? Because everything's meaningful, right? I have no zero terms here. So it was correct to, well, I don't know if it was a priori correct, but it seems to have been meaningful to have done this dense covariance estimation. And if we look at the eigenvalues of the posteriors, you see that everything is within this unit circle. So this system really wanted to be stationary. We just had to give it a little bit of help. It would be nice if we had some priors that would force it to be stationary, but we're not there yet. So I hope, as I push ahead, I hope that what this is highlighting is that when you use this system, when you use this state space, you can really abstract away all of this pymc machinery that you normally have to worry about, and instead focus on the iterative Bayesian workflow. Yeah, one of the videos I watched when I was getting into pymc for the first time was Thomas's Bayesian workflow on COVID modeling series on YouTube. And he had this idea of you start small, you add another feature, you add another feature, you add another feature. When you're bogged down by trying to reason about how do I use a scan, how do I collect default updates, how do I write the inner loop, it's difficult to do that. So the purpose of this state space module is to make that easy for you. One more note on this idea of nuisance parameters, x0 and p0. Here I'm plotting in orange the posterior and in blue the prior. So you see that there's really no information about these in the data. Yeah, pretty much you get back the priors. So when you set these, be careful. Books and I know stats models, they do something called diffuse initialization. They'll set P0 to be a diagonal matrix with like 10,000 or a million on the diagonal. That'll go away. It'll wash away in filtering. The logic is it doesn't matter because it doesn't matter. As you do Kalman updates, that P0 just sort of goes away. But what happens is you get really huge uncertainty at the beginning of your time series. So your plots are quite ugly. You'll have to chop off the first 10 or so observations. So if you don't want to worry about this, you can just set them as pm.deterministic. But just be aware that you should do kind of like a more diffuse initialization. Okay, so once again, nothing changes. We have multiple time series, but we still just call sample a conditional posterior, and boom, we get back the conditional posteriors and everything looks nice. If you want to do forecasting, rien de plus simple, call forecast, bam, you get forecasts for all of your variables. Yeah. So again, just making it easy for you to do the development loop that you want to be doing as an analyst. Now, one of the most important things about VARs and big structural models are looking at impulse response functions. And this is like you have this system of equations, and then you want to put a shock in on one of those variables. So if I put a shock in on GDP, what happens to consumption investment? Yeah. So I'm going to shock it once, and I'm not going to shock it again. I'm just going to watch how the system unrolls from that point. There's a lot of different ways to do this. So we've built in a lot of different options, and I want to go over a couple of those. The first thing you can do is just sample shocks from the Q matrix. So if you just say impulse response function with defaults, n steps is the number of steps you want to unroll the system for, it's actually going to draw samples of epsilon 0q for one shock at time 0. It's going to draw one, it's going to shock it, and then it's going to let it, and it's going to go away. So you get this kind of symmetrical behavior. Yeah, I could have drawn a positive shock, I could have drawn a negative shock. Another thing you can do is you can orthogonalize first. So you have this Q matrix and it's dense, it's full of different interactions, but you want to impose some kind of causal structure on it. So what you can do is you can rotate it so that the first row, the first variable in your model, is going to be the one that gets shocked first. So GDP gets shocked first, and then it reverberates into the second variable, which also gets a shock. And then that reverberates into the third variable, which also gets a shock, and the fourth and the fifth and the sixth. So if you have kind of a quasi-temporal causal structure in your data, this is something that's done that is quite popular. In this case, it's not so interesting. They end up being about the same, but it exists. And to do it, you just have to ask for orthogonalize equals true. Okay, the last thing you can do is you could bring your own covariance matrix. So in this case, I'm going to declare a degenerate covariance matrix with just a 1 on one diagonal position. So I'm looping over the states. I'm saying the covariance matrix is going to be a 3x3 grid of zeros with a 1 in position II. So it'll be the top left corner, then the center, then the bottom right corner. And then I'll call impulse response function, and I'll do it for all 9. So you get the whole 9x9 grid that like Stata spits out. Yeah. So this is the real GDP on real GDP. This is consumption on investment. Yeah. And you're still having this symmetrical useful behavior because I'm still passing in a covariance matrix from which shocks are drawn. You might be unhappy with this symmetrical structure. It's kind of not what you're used to seeing in an impulse response function. But that's okay. We also offer that. You can just directly define the shock size, right? Here, I'm just going to loop over and I'm going to say, I'm going to give it a vector, one item per shock. And I just say the first one is going to get a shock of 1. Yeah, the second one is going to get 0. On the second iteration, I'll give a shock of 1 to the second one, and on the third iteration on the third one. So here is probably what you're most used to looking at. These are kind of like the Bayesian IRFs that you get in other packages. I'm just looking at unit shocks. And you can see it's very easy. One line of code, a little loop, kind of get every possible cost. And then if you're a real control freak like me, you can define an entire shock trajectory and sort of build scenarios out of this. So I can say, okay, I want at time 0, I want a unit shock on GDP, but then on time 3, I want a unit shock on consumption. And this is what that looks like. Okay, so in this situation, this isn't so meaningful, but you can imagine a situation where your structural shocks have more interesting meaning, and maybe they combine in interesting ways. And so building a scenario out of them could be something neat. So we provided that functionality as well. Okay, so that's IRFs, that's VARs. I'm going really fast because I have a lot of stuff, but please remember everything's available, will be available on GitHub, I promise. And I tried to write as many notes as I could in these so that when you go back, you can extract more value out of them. I'm hoping that kind of like getting people excited to just see what you can do, because you can really do a lot of stuff. Going back to univariate analysis, we can look at this class of models called structural models, or structural time series structural modeling. And these are kind of like the go-to Lego blocks that you're allowed to compose in any way that you want. So we provide this set of components that you're allowed to put together, and then they create a linear Gaussian state space. And then you can just use that to estimate, to do any of these post-estimation tasks that we've been talking about, including time series decomposition, which will be a new task that we'll see just briefly. So kind of like GPs, if you're familiar with GPs, if you define a covariance kernel, you can add together covariance kernels, and the sum of two kernels is itself another GP. You can combine state space models by block concatenating them. And the structural model is just kind of some magic to help you do that. So for example, if you wanted to define a Gaussian random walk model with measurement error, then you would do something like this. You would say, I want a level trend component with order 1 and stochastic innovation. So this is a Gaussian random walk. And then you would also declare a measurement error. And you see that both of these are part of they're these structural component objects. What you can do with them is you can just add them together. So to make a Gaussian random walk with measurement error, you just say 1 plus the other. And the output is also one of these structural components. So you could keep going from there, right? You could add on a seasonal effect, and you could add on a long-term, like a yearly effect plus a weekly effect, yeah? And you could add on autocorrelated noise. You could put an AR2 process inside of it. And you can keep going with this and make really big and complex models. When you're done, you just call build on the result. So at any point, even one thing, right? Just that Gaussian random walk, you just call build on it and you're done. The only thing you can't call build on is a measurement error. You can't just have a measurement error. And then once you call build, you get this sort of familiar set of instructions. That's okay, you're done. Now you have a state space model. You need to tell me what is the initial trend, what's the sigma on the trend, what's the sigma on the measurement error, and you need to tell me P0. Here, there's no X0 because X0 is going to be broken up into different places. So for example, this initial trend is a part of what would have been X0. So each component can create different patterns, and there's a really exhaustive tutorial at this link where it really goes through like what do each of these look like, what do they contribute to a model, how does it look? For the purposes of this talk, I wanted to focus on kind of a marketing example because we're PyMC Labs. This is kind of like our bread and butter. I'm not going to claim that we're going to throw away your MMM, but I'm just going to show you kind of with this data how it looks. So I actually took the data generating process from this MMM example, and I used it to generate this fake sales time series. And the sales time series is a function of the past sales and also some seasonal fluctuations. But it's also a function of these control variables. So you have X1 and X2, which are advertising channels. And in principle, pumping advertising into your sales process is going to cause sales, we hope. But there's also these event spikes where something happened, a product was or something that caused some interest in the time series. So we want to model the sort of the ticking of the clock, this autoregressive process, this like policy function process, but then we also want to inject this sales stuff into it too. And we do that by using this regression component. So the regression component Tate names. And if you include a regression component in your model, you're going to get something new. It's going to say, please give me exogenous data. So I asked for a level and a trend. I moved very slowly because I turned off the shocks for the actual level. Just the velocity can change, but the actual speed can't change, except when the velocity changes. There's an annual frequency, so like a Fourier basis for the seasonality, and then there's measurement error. I compose them together and call build. PyMC model looks like a normal PyMC model. The only special thing, again, I call your attention to is that we set a pm.data and we give it the X values as the exogenous. And then we once again call build state space graph. Here's how it looks. It's sort of just a PyMC model. And we sample and we get back stuff. So you see it samples quite nicely. We get estimates for all of the different advertising channel effects. We get estimates for the measurement error. This is sort of the rate at which the trend changes. But what's more interesting than looking at the parameter estimates is actually decomposing the time series. So, okay, sorry, I'm getting ahead of myself. We do the conditional posterior. So here's our in-sample forecasts for sales. I mean, it looks reasonably okay. Probably, I mean, it's pretty bad. There's these big gaps in certain points here. And that's because we're missing some of this channel saturation, nonlinear effects that mixed marketing models pick up that we're not picking up. So again, please don't throw away your MMM. This is just an example. So, okay, what can we do? We want to look at the contributions from each subcomponent inside of our structural model. So we're going to call one more helper function called extract components from iData. And this one's a little different because we're not going to give it the iData that came back from pm.sample. We're giving it iData post, which is the conditional posterior. And all it's going to do is like add up the different bits of the conditional posterior to rebuild the actual latent states. So it's going to mutilate this states coordinate, and what you get back now is the level, the level trend, the seasonality, and the different exogenous variables. And I'm using the smoothed estimates in order to get the best possible inference on what those hidden states could be. And you see, we do okay. We get the seasonality. We totally flunk on the level, and that's because we're misattributing level. We are too low on the effect of the sales channels, and we're instead giving credit to the actual like time series level component. So it could be a prior thing. It could just be, like I said, because it's not its marketing model. But this is an example of how you can do a big complex model and then pull it apart and see how the components look. Now, a new thing we can do is, because we have exogenous data, we can do scenario-based testing. So we just run the function forward and we have to put something in there. We have to tell it what's the sales in new time. So what we'll do is we'll forecast and it'll say you cast, you used exogenous data and you have to give me. So this is kind of cool. We have the power to feature insertions. Scenario one, if I the advertisements, if I just pass a matrix of zeros as my scenario and I run it for 20 periods, I'll get something. I could set both of these scenarios to just their mean, their in-sample means. So what if I spent the average on both of these sales channels, and I could make a forecast out of that? Or I could say, okay, what about this X1 channel? I'm just going to set to its absolute maximum. So whatever the maximum was in sample, I'm going to spend that much on the X1 for 20 periods. How does it look? And so I kind of plot these conditional forecasts together. Red where I did nothing, yellow where I did the mean, and green where I maxed out one of the channels. And you see how we always capture that policy function dynamics, the sort of seasonal dynamic, the level change dynamics. It's very hard to see, but the confidence intervals are actually growing here slowly. But then we also get these level shifts that come from the scenarios. And had we had time varying parameters, which is totally allowed, I glossed over this point, but when we declare the structural model, I said innovations equals false on the regression component. Excuse me. And what innovations means is, do you want stochastic shocks on the regression parameters? Because the regression parameters are hidden states, and they're being multiplied by the data that's coming in externally. That's why when you saw the hidden state decomposition, these are all flat lines, because these are just constant parameters. They're not being shocked at all. But if you were to go back and say, no, I want shocks, then these would be moving through time and event variables. And when you do your forecasting, you would also see changes that come from uncertainty and what those parameters could be doing in the future. Okay, so that's a lot. And if you've bared with me for all that, I appreciate it. I have one more subject with 3 minutes to go or something, so I'll go very fast and talk about a custom state space model with kind of a very complicated setup. So like kind of push this as hard as I can, yeah. In macroeconomics, we sometimes want to write models that have what's called micro foundations. So we don't just want to fit a var. We want to fit a model that starts from what do people do? What do they want? There's this whole thing called the Lucas critique, and it's very important, and people talk about it. And it spawned this class of models called DSGE, Dynamic Stochastic General Equilibrium. Of those models, the simplest, maybe one of the simplest, that's non-trivial, is called the real business cycle. So how does this model look? If you want to look at the math, please feel free. But you have to describe what agents in the economy want to do, what are their constraints, how do they behave, and you do this nonlinear optimization, and you come up with a system of nonlinear equations that looks like this. And so you say, well, this is we're fixed. This is a linear Gaussian system. What do we do? It turns out that this setup is still amenable to models like this, because models like this can be linearized. So what our strategy will be is to take this nonlinear system to find a stable point in the system where we know the values, because we can't compute anything here really, but we can find a point where nothing changes if we turn off all the shocks and we compute what's called the steady state by sending all the parameters to sort of a fixed value, and then find a linear approximation around that steady state. That as long as our shocks aren't too big, we'll have a faithful reproduction of this nonlinear system in our linear Gaussian setup. So I kind of describe what the steps for doing this are. I'm going to use SymPy here to type in all of these equations, and I get this vector of nonlinear equations. I ask you, please just trust me. Here are the steady state equations. So now for each of these, I can express it as just a function of model parameters. And these model parameters aren't like just the regression coefficients. Yeah, they have actual economic meaning. And that's why people want to fit these kinds of models. And then I compute Jacobians, take systems of partial derivatives for each one of these. For the system of nonlinear equations, I take the derivative with respect to the t-1, t+1 variables and cast it into the steady state. You get something that looks like this. So this is an 8x8 matrix that's full of stuff. And then I have some magic to turn SymPy into pytensor. So here is the pytensor matrix, and here is the here's the SymPy matrix of symbolic representation, and then here is the pytensor, the graph representation. And then we're going to use this perturbation algorithm to find the policy function that's implied by implied by this nonlinear system. So I have to plug that in with a custom pytensor op. And that means we're going to lose gradients. So I'm not going to be able to use nuts to sample this, but that's okay. So, okay, fine. So the point is here is that you can do a ton with this. And what you can do in the end is you can wrap it all into a state space. So I make an RBC model, I call it a subclass of pymc-statespace. I'm going to tell it how many states there are, how many shocks there are, and how many observed variables there are. And then I'm just doing all that computation I showed you very, very quickly inside of this model and saving the results as member variables and calling the superclass constructor. Now, the real magic happens here in this make symbolic graph method. So the make symbolic graph is the place where the state space model actually knows to look for a variable called alpha, to look for a variable called sigma c, and knows how to plug it in to the internal representation. So the representation is stored in this thing called SSM. And so for the transition matrix, I'm plugging in T, which comes out of this perturbation solution. For the selection matrix, I'm plugging in R and so on. And the rest of this is kind of syntactic sugar. There's a very thorough notebook that goes through what all this means. What does param names do? What does chords do? What does params info do? But basically, these are all the bits that are inside of the state space system, as long as you can fill out this make symbolic graph, which just says, what should I look for? And then where should I put it? Once you've defined that, then you can use it like we've seen with any of the predefined ones. I create an RBC model with an observed state, and then it barks at me, please define all of these, because I told it that that's what it needs. So I could set up a model and I can sample, again, I'm doing like a sample one trajectory from the DSGE. And here's what my fake GDP looks like. This is why people like these models, because you get these like sort of nice business cycles. And then I'm going to use the SMC sampler because I can't compute with gradients, but I'll just declare all my priors. I'll build a state space graph and I'll call sample SMC, and you see that it works just fine. I recover value for the standard deviation of the shocks, which is what we're looking for. There's not a lot of information in these models about some of these deep parameters, but we're very happy that we recover sigma epsilon. And from there, you're free to do you get all of the machinery we saw. I can do conditional posterior estimates. I only fit the data on Y, but I get hidden state inference on all the other economic variables, the number of hours worked, the amount of consumption by households, the capital stock and economy. And I can do impulse response functions. So you have this big complex system. As long as you can get it to a linear form, which I think pretty much every discipline has linearization tricks in their toolkits, then you can get it into this state space representation, and then you gain access to all of this nice machinery. So that's kind of it. That's like the high level of everything you can do with the state space package. There's a lot more coming, more prepackaged models, more default priors to make things even more convenient for you, more multivariate structural stuff. So hit watch on the pymc experimental repository if that sounds interesting to you. Or like I said, if you have a desire to help out, please do. Or if you try it and you hit bugs, I guarantee you there's bugs in this, please open an issue and I will love to work with you to fix them.
Very cool, Jesse. Thank you so much for that. Really in-depth, really clear, and yeah, showcasing functionality that was completely new to me as well. So I learned a lot. We are over time, but nonetheless, like there's some really great questions that I want to make sure we get to. And we are recording anyway, so even if that person left, they'll be able to see it on the recording. So Dan Weizenfeld, good to see you here, asks, does the recommendation for JAX apply to any pymc model that uses scan, or just models in the state space module?
Yes, any model that uses scan together with either linear algebra or multivariate normals, which I repeat myself. but that appears to be where the bottleneck is. When I was just scanning, if you're just scanning over like a unidimensional Garch or like an ARIMA or a SARIMAX, you should be fine. You can use whatever backend you please. But definitely reach for JAX if you're doing anything with matrices.
Nicolo asks, will there be in the near future the possibility of estimating non-Gaussian models as well as using a state space function like Garch?
We would have to implement some kind of particle filter to do the Kalman filtering. Or we could throw away the Kalman filter and try to bring some of this machinery to a more broad setup. I guess that would be kind of the goal. I would call that a long-term goal, though.
Margaret asks, is there a way to use this model as a set of independent and finite time series, but all connected? Think of an airplane booking for a given route. Each day, a different flight departs, and booking happens since 1 year before. Or sports ticketing, a team sells tickets for each match in their stadium.
Sounds complicated. It sounds like you would break my recommendation of staying under 50 states. I would need to know more about the specific setup, but like I said, as you can write it down as like a linear system, you can estimate it. Like if all of those, if every booking desk was sort of a latent state, and then they could be correlated through some kind of like economic process, right, where there's commonly shared shocks that would increase all of them and idiosyncratic shocks that would increase some of them. You could imagine sort of building from this start, if I understand well.
Foreman, also great to see here. He asks, is there any way to do online updating of the model? For example, if I train weekly with updated data, can I start from previously fitted seasonality and extend it, or will I need to train from scratch?
Train it from scratch. It's a limitation, known limitation of pymc, which is, it's a shame, right? Because the whole promise of the Kalman filter is iterative updates. And then I'm here to tell you that you can't do iterative updates. But yeah, limitation of pymc. There's some cool stuff. Adrian is doing some cool stuff with starting and stopping sampling in NetPy. I don't know if you can hot swap data doing that, but you can at least like pause sampling and like interfere with the system, but then you'd break detailed balance. So I don't know, probably not.
Probably not. Vishal asks, for structural models with multiple related time series like var, do you use the structural module? Different approach?
I very strongly recommend the structural model for multiple time series. That's a place where it gets really hairy with the scans. You can run into all this stuff of like, because when you're doing the scan, pymc is building a forward graph that sort of describes how to generate data. And then it's smart enough to kind of work out what's the probability that's implied by that. But that requires it to know how to map from this generative process to this probability process. And when you do matrix multiplications, you're mixing stuff together, and addition and probability distributions kind of don't go together. Like it turns into convolutions, and you need to know closed form results, which is not good.
Justin asks, related to questions above, with var models, we assume that time series are modeled based on the history of all series, correct? What about cases where multiple time series are expected to behave similarly but not share history? The way to impose a hierarchical structure on the weights of the AR models.
100%. Yep, 100%, 100%. Like I said, you are totally free to do anything you want until you have to declare AR params, like PM.deterministic AR params. So you could make every single one of those numbers that goes into that matrix by hand, and you could build that matrix by yourself with as many zeros as you want, or with blocks, correlated blocks, right? You have these like Minnesota priors where the diagonal has a certain prior and the off diagonal is a scaled version of the diagonal. So you can really get creative here. And that's why that has this structure where you're asked to build these priors by yourself so that you can get creative and you have the space to do that.
And if he lets the power of doing this in the pymc framework, right? Similar situation with GP, there's like specialized GP libraries that sometimes are faster, but then you can't really combine it with this other rich toolbox of building models, and with time series, it's the same, right? Like hierarchy is, I mean, yeah, that's just naturally supported already, and you can just combine that and have that be a small piece of a lot larger model and bring these things together. Follow-up question from Justin. Book recommendation for a state space model, especially if there are any that lean Bayesian.
Again, I missed the first word of that. It was the important word.
If you had one book to start with for learning time series modeling and state space framework, what would you
yeah,
recommend?
yeah. It's Durbin and Koopsman. Time series analysis with state space methods. That's the Bible. It's in the doc. So if you read the documentation for the state space module, I cite it over and over again. So the citation's in the code.
And next question to Bruno. Is there a way to generalize away from Gaussian diffusion and have nonlinear dynamics happening inside the system? GDP and consumption are well behaved relatively to certain other variables like liquidity and demand supply bursts.
Yeah. You would like to be able to build it in like Poisson jump diffusions and things too, right? Again, it goes back to this trade-off between the full power of pymc and the sort of Gaussian linear structure that gives you this nice filtering and this nice like hidden state inference and whatnot. So the answer is you can do all that already. You just have to get your hands a little bit dirty. And if you want to do it, open a thread on the discourse where we all hang out, and I'm happy to try to help.
Cool. And then last question from me is, what do you think is the timeline from getting this from pymc experimental to pymc proper or its own library?
I have no idea. I don't know. Like pymc experimental, it's like, it's just like a black hole sometimes. I don't know. It's getting there. So for a long time, it really was experimental. And I've done a big round of bug fixes, and I'm very thankful to NumFocus for a small development grant to have a little bit of money to be able to tidy some things up and get it to a place where I think someone could use it for a real industry project. And I wouldn't be ashamed to say that they were doing that, or shocked to hear they were doing that, maybe is a better way to put it. But there's a few more I's to dot and T's to cross. The conditional forecasting, for example, is actually not in. I ran that on a development branch. It's currently an open PR. So there's active work going on, a few more things to do. I would love to see it in pymc for real, like in the next year. That'd be cool.
Sure. Oh, and then there was actually one other question about once you have the posterior, which is probably my favorite question ever. How do you integrate a reward function to aid in something like developing pricing schemes? So I'm gonna answer that one. That is Bayesian decision analysis, BDA, and there's a great blog post by this Thomas Wiki guy. I posted the link here, twiki.io, and the title of the blog post is Using Bayesian Decision Making to Optimize Supply Chains. So yeah, that is really cool because what good are posteriors if you're not using them, right? So this is a way to actually use them to make better decisions, and you will always make better decisions if you take your full posterior into account. And I guess then to conclude, like if this functionality seems relevant to you, we'd love to work with someone on this, solving these types of problems. This is really state of the art stuff. And yeah, if we have an interesting industry application that could be a consulting project, that'd be really fun to work on, to test the tooling, develop the tooling, and of course solve applied problems. That's what we're here for. And yeah, with that, thanks everyone for tuning in, especially if you stuck around longer. And Jesse, thank you so much for sharing your knowledge and for writing the code in the first place.
Yeah, it was a pleasure. Thanks everyone for coming.
Thanks. Bye, everybody.